Hello again, everyone. This video will cover infrared methods and instrumentation. We're going to look at some ways to do infrared spectroscopy. In particular, we're going to talk about a thing called the Michelson interferometer. We'll discover that infrared spectrometers mainly work by Fourier transforms. We'll have a quick discussion about that. Look at how to prepare some samples and discuss a couple of applications. So perhaps the first thing to start with is just to point out that infrared spectroscopy is an absorption-based measurement. So just like UV vis, however, with electromagnetic radiation in the infrared part of the spectrum. So infrared light is brought upon a sample and the amount that is transmitted is measured. The difference is what's absorbed, and that's how you get an infrared absorption spectrum. So up until sort of the 1980s, most instruments were similar to UV vis instruments in that they used gratings and slits, like in the little diagram shown here. So light would be dispersed off a reflection grating and wavelengths selected by positioning a slit. These days, all infrared spectrometers are Fourier transform based, and they have a number of advantages over dispersive instruments, which we will quickly run through. The first is, I think, fairly obvious, that gratings, which form part of devices called monochromators, can only select one wavelength at a time. So you have to scan all the way across. If you use an FT-IR instrument, all wavelengths are available simultaneously. And that's thanks to the Michelson interferometer, which we will be meeting soon. And because there are no slits, measurements are much faster when using an FT-IR instrument. You also have fewer mirrors and other optical items, which means your losses are lower and signal to noise ratio is up, which is a good thing. So you can do much better measurements using the FT-IR approach. Another really beneficial advantage is in instrument resolution. FT-IR instruments typically have superior resolution to dispersive instruments, and that's because the resolution with a dispersive instrument is determined by the number of lines that you can rule onto the grating to do the dispersion. However, with the FT-IR instrument, as we will see, a key item in it is that there is a moving mirror. And the resolution that an FT-IR spectrometer can achieve just depends on 2 times the distance that mirror moves. So the 2 just comes from the fact that the light goes up and back down that path. So to improve the resolution in an FT-IR spectrometer, just move the mirror further, and so you can build quite a long track to do that and get really high resolution spectra. So here's an example of the difference between a dispersive instrument, typical sort of spectrum, broad features. The resolution is about half a wave number. That's the blue spectrum here. So this one. With a really good high resolution FT-IR, say with the moving mirror being able to move a few meters, you can get really fine detail. These are not just broad bands. So in this spectrum here, the resolution is down to a fraction of a wave number. And you can see that they're not broad bands, but there's all of this extra structure on them. And we can expand this up take a little slice there and have a look. And this is rotational information now being resolved here. Now, it's a bit hard to see, but if you look at the x-axis, that's one wave number. So the resolution there really is a fraction of a wave number, and you can see that there are clear spikes all the way along. These are rotational energy levels, which are superimposed on each vibrational level. So just as we saw that each electronic level had a series of vibrational levels associated with it, each vibrational energy level has a whole lot of very fine rotational energy levels within it. So that's what we see here. You can actually resolve that out with a good quality FTIR instrument. Final advantage is one of precision, and that's because FTIR spectrometers use a laser for inbuilt calibration. It's not so important, but might as well tell you. Typically, this is a helium neon laser. That's what the HENI stands for. And this was actually the first laser to be commercialized back in the 1960s. Anyway, it typically produces a nice red beam, such as shown in the picture there, but you can nowadays get, actually you can get quite a few different colors. The green version is affectionately known as the Greenie laser. So in combination with the Michelson interferometer, the built-in calibration laser ensures that the mirror moves perfectly in a nice steady way, and you get a high precision measurement. Finally, the FTIR instrument can do a broad range of wavelengths. So this is another annoying thing about dispersion gratings. You need different gratings for different regions of the spectrum. However, the FTIR instrument, you can just pump through all the wavelengths at once. And we'll see how you do that right now. Okay, so let's meet the Michelson interferometer. This is a very useful, very simple piece of kit which has been around for a while. It's over 100 years since the Michelson interferometer was invented. The key to it is here. This is a 50-50 beam splitter, and it's positioned at 45 degrees to the incoming infrared light. So when the light hits that beam splitter, half of it bounces off right here and half of it passes through. And mirrors are positioned to reflect these beams straight back from where they came. One of them is fixed at some distance away, and the other is a moving mirror. So the light reflects off them back towards the beam splitter, where it's recombined and heads out towards the detector. Okay, so the kind of sources that you can find, the mid-infrared is the most used part of the infrared spectrum, and a very simple little device called a glow bar made of silicon carbide. You heat it up and it produces a nice lot of infrared light, which can be focused in towards the beam splitter. If you want to go into the far infrared, a mercury arc lamp is good for that. And if you've got deep pockets or a great idea that can win merit-based beam time, you can go over to the Australian synchrotron across the road and use the infrared beam line there. So the synchrotron produces quite a lot of radiation in the infrared part of the spectrum. The infrared beam line at the Australian synchrotron is really bright, and it can actually pass through millimeters of water. It's so intense. Okay, so this just explains what I said on the previous slide. The key point to take away here is wavelength information is very simply encoded because of the moving mirror. So the distance between the fixed mirror and the beam splitter doesn't change, that's L1, but L2 does change, and so this difference between L1 and L2, of course, can be divided by the wavelength of the incoming light. So whatever that distance is, different wavelengths will fit, if you like, differently into that distance. So if you can imagine a little wave coming back along here, it's going to interfere when it recombines and heads out to the detector. And depending on what the wavelength is, so we're talking about now, the number of wavelengths that can fit into that distance, depending on that phase matchup, you will get a different interference pattern for different wavelengths. So you can shine a whole lot of wavelengths in at once, and they will interfere with themselves and each other differently. So that's how that's how information about different wavelengths is encoded into what passes through the sample and onto the detector. So here's now a box diagram for a whole FTIR spectrometer. So the Michelson interferometer is up here. That's part of the spectrometer. The static mirror, moving mirror, the infrared source. This is the infrared source. Let's say it's equipped with a glow bar. The light comes out of the Michelson interferometer through the sample to the detector, where it's then post-processed. This is where the Fourier transform bit comes in. It's post-processed, and then out the other end, you get your spectrum. Now, there's the laser over on the side. If you remember, one of the advantages of using FTIR spectrometers is that they contain a laser, and this helps keep everything nicely in line. The laser is bouncing off the back of the moving mirror here, so it's coming in and it follows along the moving mirror to make sure that everything's moving nicely. It's not the light source. Don't get confused there. The light source is a glow bar or the synchrotron, for example. Okay, let's have a quick discussion about sample prep. So gases, very easily done in these pressure cells. If you remember, absorbance given by Beer-Lambert law. So while the concentration in gases is quite low, you can increase the path length to get more absorbance, to be able to do a nice measurement. Plus, you can also, if you have a reasonably good quality gas cell, you can increase the pressure in there as a way to push up the concentration, but it's better just to use a longer path length. So gases are easily handled. You can fill up a chamber like this with the gas of interest, seal it up, and pop it in your spectrometer. Solution phase measurements can be a bit more problematic. They're very convenient. If you have a sample, you can just dissolve it up in a solvent, pop it in a cuvette, and measure it in the spectrometer. However, the catch is that a lot of solvents absorb infrared. So you need a solvent that is transparent in the region of interest. Water is especially bad for this. It's quite poor. There's a lot of infrared wavelengths that are strongly absorbed by water, particularly around that 3000 wave numbers, thanks to OH. But there are some solvents, for example, chloroform here is a useful solvent. There's quite a lot. Those blue lines indicate the regions where it's transparent. There's quite a lot of transparency there in the infrared for chloroform. Some solvents are not great. Dimethylformamide has a huge absorption in here, so that's no good. You can sometimes work with a neat sample of pure liquid. You can just pop it onto a salt plate. You probably haven't seen these salt plates now. We used to use these salt plates in labs a lot, but everything's been replaced by ATR, the attenuated total internal reflection infrared instruments, which we'll talk about in the lecture. But before they came along, you used to have to make these salt discs. So of course, that meant that you couldn't do aqueous samples. That was a big no, because you would just dissolve the salt disc. But if you had an oil, if you had a pure liquid that was oily, you could pop it on the salt disc and stick that in the infrared spectrometer. So the way you made these pellets was by pressing the halide salt under really high pressure, because they have this really nice property called cold flow, which means they become transparent once they're placed under enough pressure. So that's how you make the salt disc. But then a neat thing to do is to get the analyte. If you have a solid sample, you grind up the analyte with the salt. So you make a powder that's got the analyte mixed in with salt, and then you press the whole thing together, and you actually produce a nice little disc with lots of analyte in it. And then you just do the measurement straight through that, and the analyte absorbs, and you get its spectrum. Now, if you can't get your solid directly into a salt disc, it may be you can't grind it fine enough, or it just won't, the disc just won't press out. You can get your solid sample and dissolve it in a mineral oil and make what's known as a mull. And that mull can then be placed between two salt plates, the same as you would a liquid phase. And you can measure a spectrum that way. There we go, a bit of useful advice for you. It's a salt disc. If you stick your fingers on it, it'll start to dissolve and you'll cover it in oil. And all that you'll ever measure is the infrared spectrum of finger grease. Okay, so you've got the instrument, you've made your sample, you put it in. What is outputted is a thing called an interferogram. This is the interference pattern created by the Michelson interferometer, which then has passed through your sample. Some of the light is absorbed and what is transmitted is detected. So it looks a bit funny, a bit like this, but in here, all the information about which wavelengths have gone through and how much they've been absorbed is contained. Now, you have to do a bit of maths to pull this out. You can't just look at it. I have not met a person yet. Maybe there is somebody out there who can do a Fourier transform in their head, but I've not met anyone yet. All you need to know is that the instruments usually have software with them, which does this for you. So you won't have to do one, just be aware of what it is. It's a mathematical procedure where the data is transformed from the time domain to the frequency domain. So the time domain information is there because you have a moving mirror. So light takes different amounts of time to get to the detector. Within that is frequency domain information. We want the frequency domain because the frequency is proportional to the energy. So that will tell us which energies have been absorbed. And it's the Fourier transform that lets us do that. This is essentially what happens. A little black box. Interferogram comes in, so this has gone through the sample to the detector, and the detector gets this interferogram. That's what's measured. It goes in to the software which does the Fourier transform calculations. Your guess is as good as mine what the first F stands for in this little box. Fast, maybe? And once the calculations are done, the spectrum is outputted. Now here it's shown as percent transmittance. So we've got our frequency domain information, wavelength if you like, wave number, however you want to express it. We've got wave number here and the amount that's transmitted, 0 through to 100%. So we can see where the absorptions have occurred. All right, just finish with a couple of practicalities about measuring spectra. Other absorptions can contaminate, if you like, or affect the spectrum. Atmospheric water is a common source of additional absorption. Carbon dioxide in air, as we'll see in the next lecture, carbon dioxide absorbs very strongly in the infrared, although I'm pretty sure you all know that. In fact, I think everybody now knows, thanks to all the discussions around climate change, that carbon dioxide in the air absorbs infrared. It's just, unfortunately, we have a few key political figures who just seem to willfully ignore this well-established scientific fact. Some optical components, or even the sample holder, if you are using glass rather than quartz, for example, that can absorb. So the easy way around this, of course, is just to take a background spectrum. So here's our background or reference. Subtract that away from what's generated from a single beam, and then you get the transmission spectrum afterwards, after having done that. Okay, now for just a quick discussion on a few applications of infrared spectroscopy. Here's one that you're probably familiar with. You will have experienced it. Hopefully, it didn't turn out badly for you. So the little roadside breath test device uses FTIR. It measures the alcohol content via infrared because ethanol has this nice OH group, which gives a very strong signal in FTIR. Now, it's an interesting question as to how specific this is. I mean, plenty of compounds have a strong OH absorption. Here's one, menthol. This turns up in cough drops. Look at that. So, don't want to give you any ideas, but hey, next time, if it's not looking good, you could always just try and argue with the nice police officer that menthol contains an OH functional group, and as luck would have it, you'd just eaten 16 packets of menthol cough lollies. Good luck with that. Forensic scientists are often faced with unknown samples, and they could be a mixture. They really do not know anything about them. And so combining a separations technique with an identification method is a smart way to go about it. FTIR is quite good at identifying. So it can be combined quite readily with gas or liquid chromatography. So you use the chromatography to separate out the components, and as each component comes out off the chromatography instrument, it can be fed straight into an FTIR. You can have FTIR spectra being constantly measured as material comes out of the chromatography column, and the components of an unknown mixture can be identified. Of course, mass spec is another excellent method to combine with GC or LC for identification. Well, here is a selection of substances which I truly hope none of you ever encounter. 3 particularly nasty gases here, but there are some evil-minded, malicious types who use these, and that means that there are some wonderful forensic scientists who have to be involved in identifying these gases. GC-FTIR is quite useful for this because, being gases, they can be isolated with GC and readily identified using infrared. So we have here sarin, which unfortunately has been in the news recently. Assad used sarin in some attacks on people in Syria. Before that, sarin was used in the Tokyo underground attack back in the 90s. VX is another very nasty nerve agent, and I think it was a derivative of VX that was used in the recent alleged Russian poisonings in the UK. And mustard gas was the chemical gas that was used extensively in the First World War. All 3 of them very, very nasty. Now, they all contain some key functional groups which give signals here in the infrared, but down in this region, the so-called fingerprint region, the molecules are sufficiently different and unique that they can be identified. So small amounts can be identified using infrared. Now here's a much more useful and down-to-earth application. You will have done this, I'm sure, at some point. In synthetic chemistry, infrared is a quick and convenient way to monitor how your reaction is going. If you're trying to install a key functional group into your substrate, you can monitor how that's going by looking for its absorption. This little device here is a nice one for real-time reaction monitoring, so a useful little device. Nice little 3-necked round bottom flask here where there is a probe, reactant mixture being fed in, and that can be sampled and monitored as the reaction proceeds. So here are some of the frequencies for key functional groups. You don't need to memorize this table. We've got much better things to ask you in exams than to regurgitate frequencies of functional groups. However, ones that are worth knowing are the oxygen ones. So single bonded OH is up around the 3000s. 3000 to 3500 typically, wave numbers. And the double bonded oxygen, the carbonyl functional group, gives a very strong characteristic signal in the low 700s typically. So those are ones that it's probably worth knowing. Single and double bonded oxygen groups in molecules.